In section 2.4, our goal is to use properties of algebra. In this section, we'll be starting to talk about what's called deductive reasoning. We have skipped over section 1.1, which we'll talk about. It relates to inductive reasoning. Your inductive reasoning is reaching conclusions based on what you observed, based on patterns. So if 3 people walked into the room with dripping boots carrying umbrellas, there's something we could deduct using our inductive reasoning based on patterns. What we're going to use in geometry the most is called deductive reasoning. This is the drawing of conclusions and giving reasons based on a rule, based on a fact. For example, if I wrote 2 times the quantity of x plus 3 equals 2x plus 6, I know that based on the distributive property, which we'll use in our proofs. That's a rule. This is deductive reasoning. We want to make sure as we use deductive reasoning that we're not making any assumptions. So we're going to look at some given information, some pictures or some pictures along with a statement, and figure out if we know that some statements being made are true or false without making any assumptions at all. So assuming statements from pictures, we are given this picture in number 1 and only the picture. They didn't tell us anything else. Statement A says the length of AM plus the length of MB equals the whole length of AB. We're trying to figure out if this is true or false without assuming anything. This one is true. That is our definition of the segment addition postulate that states if you add one little segment plus the little one next to it, it adds up to the whole large segment. Statement B says the length of segment AM is equal to the length of segment MB. Now, I need to be careful because we just got done working with some statements like this. However, in those we were always told that M is a midpoint. I don't know that M is a midpoint, even though it looks like it is. I cannot assume that, so this one is false. Number 2, we are given this picture over here. We are also given a statement. This says ray OB bisects angle AOC. So we are given this statement and the picture that goes with it. Now they did tell us the OB is a bisector. It cuts angle AOC exactly into 2 parts, which means that angle 1 and angle 2 should be congruent. Statement A, the measure of angle 1 equals the measure of angle 2. Because they told us this is a bisector, that is true. If they had not told us it was a bisector, I cannot assume that it's in the center. Statement B, the measure of angle 1 plus the measure of angle 2 equals the whole measure of angle AOC. Like the segment we just looked at, this is our angle addition postulate. It states that one angle and an angle adjacent to it adds up to a large angle. This is also true. Number 3, we are only given the picture. They did not tell me any other information. I don't know if anything's a bisector or a midpoint, just the pictures of the angle. Statement A, the measure of angle 1 equals the measure of angle 2. Now this looks like the picture we just worked with, but since they didn't tell us that ray OB bisects anything, this one is false. I cannot assume it's in the center. Statement B, the measure of angle 1 plus the measure of angle 2 adds up to the measure of angle AOC. Again, that's angle addition, and that's always true. Statement C, the measure of angle AOC is 90 degrees. Well, now that does look like it's a right angle. However, they did not tell me it was 90 degrees. They did not draw the square in the corner to show that it's a right angle. So this is false. I cannot assume it's 90 degrees. It might be 89.9. As we work through starting proofs, which will be starting this section, we're going to use some real number properties. The first one is addition, and when you read these will be conditional statements. The first part is true, and it's saying if I know the first part is true, then the last part must be true. So for addition, if I know that 2 things are equal, A equals B, then if you add the same amount to each side, if I add c to both sides, this states it must still be equal. So if I know that a is 1 and b is 1, they're equal, and we add the same amount to both sides, maybe we're adding 2, then they'll both be 3. They'll both still be equal. So if a equals b, then a plus c equals b plus c. We'll use this as we solve equations. If you add something to both sides to get the next answer, then the reason for that next answer is our addition property. The same works for subtraction. If you know two things are equal, and we're just going to call those a and b, and you take away, you subtract the same amount from each side, then they're still equal. We also have a property of multiplication. So if I know two sides are equal in an equation and I multiply both sides by the same thing, so I had a equals b, if I multiply both by c, the two sides will still be equal. This also works for division as long as I'm not trying to divide by 0. So if a equals b, then a over c equals b over c, as long as c is not 0, because that's undefined. You need to know these properties and be comfortable with them because we're going to be using these for proofs. One thing that's highly recommended to geometry students is to make flashcards to help you learn the names of the properties. Our next property is called the reflexive property. It says if I have a, then a is equal to itself. The way you can remember that this is the reflexive property, something equal to itself, is if you look in the mirror and you see that mirror image of yourself, it's the same, and that's your reflection. So reflexive shows you something that's the same. The next property is symmetric. The symmetric property lets you switch the order where things are on the two sides of the equal sign. So if I know that a is equal to b, then I can switch it and write b equals a. The transitive property. If a is equal to b and b equals c, then a and c must be equal. What you're doing is you're cutting out the one that repeats and linking these two together. If a is equal to b but b is equal to c, then all three are the same and a and c are equal. Substitution. If a is equal to b, then a can be substituted for b in any equation or expression. This is like me saying x equals 3 and giving you an equation. You would take the 3, plug it in for x. The reason we can do that is you're substituting. You're substituting that value in. Okay, so we're going to work some sample proofs, and I want to talk to you about how proofs are set up, and we'll do 3 of these. We're going to start proofs with equations, and then in class what we'll do is we'll do some example geometric proofs that will help you be more comfortable with those. We are going to do proofs in what's called a 2-column proof. So it kind of looks like a T-chart. 2 columns, a line down the center. The left column is your statements, all of the things you know. And your right column is your reasons. Everything we do in math has a reason. We're going to list those. Your statements and reasons should both be numbered. And if I look at this numbered 1 statement, I can look over at a number 1 matching reason. This is how you got that statement. The only thing we know to start is what they told us is true. So I'm going to write down 5x minus 9 equals 3x plus 7. The reason I know that is because it was given. This other word will never ever appear anywhere in your formal proof. Now, to solve this, what we're going to do is we're just going to work through the steps of an equation. Most of you would subtract the 3x. And so we're going to kind of do that as an in-between step, and I'm going to write down my next formal step in the equation. So 2x minus 9 equals 7. Now, my reason for statement number 2 is what I did to number 1 to get this one. Okay, so looking at the first statement, I subtracted 3x from both sides. So I know 2x minus 9 equals 7 by the subtraction property. And I'm just going to abbreviate property. Okay, then we'll do our next step in our equation. So we would add 9 to get all our numbers together. so that our next statement is 2x equals 16. And again, my reason for number 3 is how I got this from the previous step. So to get from 2 to 3, we added 9. So this is our addition property. And I'm going to abbreviate property. Then if you solve the equation, we get x equals 8. And we would get that by dividing both sides by 2. So this is by the division property. And if you look, you know that we're done with the proof because we got what we were trying to prove. The proof is what you're trying to get to at the end by doing steps and giving reasons. My last statement exactly matches what I was trying to prove, so I know I'm finished. Let's move on to example 2. Again, all of these will be T-charts. We're going to do all of our proofs as 2-column proofs. The left side is your statements, and the right side is your reasons. We always start with what we know. So 2a minus 6 equals 4a plus 10, and my reason is that it was given. Make sure your statements are always on the left and your reasons are always on the right. Do not switch these. Then I'm going to go through and I'm going to start solving my equation. Now 2a is smaller, so I'm going to move that over. And I'll have negative 6, don't lose that negative, equals 2a plus 10. To get from step 1 to the step 2, we subtracted the 2a. So this is our subtraction property. My next statement, I'm going to move my 10. So I have negative 16 equals 2a. I got this by subtracting 10. So it's okay to have 2 in a row. You might have 2 subtractions, 2 additions, 1 of each. My last statement, if I divide by 2, I get that a is negative 8. And I got that by the division property. Now, if you solve this the other direction, sometimes people move things differently. If you put all your a's to the left and your numbers to the right, you would have ended up with a equals negative 8. Not in order that they asked us to solve. If you get that at the end, you can always switch it around. So if I had a equals negative 8, I could write a negative 8 equals a. The one that lets us switch the order is the symmetric property. Okay, I want you to go through and try solving this equation. And I will check these when you come into class. I want you to go through, and if it helps, one thing you might do is just on the left-hand side, doing one step at a time. Solve the equation out step by step by step, and then go back and try to fill in your reasons. Remember, your first statement is this equation that we're starting with, and our first reason, always for proofs, is given. I want you to go through and solve this one. Think about how you knew you could do each step and list that reason. We'll check those when you come into class. And then we'll be working on page 99 to 101, numbers 4 through 8, 10 through 23, and 41 to 50, and that is all.